Okay, so we've been looking at these compound angles. Yesterday we talked about compound angular surfaces, which was if we had a block like this and we needed to mill the corner off of it. It was telling us how to rotate that block and tilt the table or put it on an angled vise in order to get that surface here that we're milling level to the head of the mill. And really the most common way we're going to run into that is looking at a front view and a side view. We're on the front view. We might be told that this is an 18-degree angle. That is the view of this side right here. And on an end view or side view, we might be told that this is a 31-degree angle. Now, just like with our drilling, when we were not given the thickness, if we were just given the two angles from the different views, we could pick one of the dimensions. Remember, the actual dimensions don't matter. That's only if we're looking at like cutting time and stuff like that, which we're not here. We're just looking at that angle of rotation and angle of tilt here. What matters is the ratio of the dimensions. So we can pick one of the dimensions and use that to find other hypothetical dimensions for the rest of them and go from there. So I am going to pick this thickness here. So from here to here and here to here. A little bit long. Typically, I pick it to be a dimension that's easy to work with. 10, 100, something that is going to keep me from doing a lot of round off. So let's just pick 10 millimeters for that thickness, for that depth. From that, we can calculate these other dimensions. So this dimension here, I'll call dimension A. Off of my 18-degree angle, the 10 is the opposite side. A is the adjacent side. So I'd be dealing with a tangent. Tangent of 18 degrees equals the opposite of 10 over the adjacent of A. We'll put that over 1 and we will cross, multiply, and divide. So that's going to be 10 times 1, which is just 10, divided by the tangent of 18. Make my modes set correctly here. Yes, 30.78 millimeters. Next, we'll come over here to the 31. We'll look for this dimension here, which I'll call dimension B. And again, according to the 31, the 10 here is the opposite side, B is the adjacent side. So we're again dealing with a tangent. The tangent of 31 degrees equals that opposite side of 10 over the adjacent side of B. And once again, we'll put it over 1, and we will cross, multiply, and divide. So again, 1 times 10 is 10, divided by the tangent of 31 degrees. Gives us 16.64 millimeters. Now that we have those dimensions, if you recall, our angle of rotation comes off of the top view. This dimension here is just B, and this dimension here is just A. This is 30.78 millimeters. This is 16.64 millimeters. And my angle of rotation is right here. That's R. So So we can find that angle of rotation, because what we have here is the opposite side and the adjacent side again. But since we're looking for the angle, it's an inverse tangent of our opposite side of 16.64 over our adjacent side of 30.78. Inverse tangent, second tangent, 16.64 divided by 30.78 gives us 28.396, 28.40 degrees, we'll call it. That is our angle of rotation. So that's telling us that on the table for our mill, we need to turn that part 28.4 degrees off of a perpendicular in order to line that side up so that we can rotate it on the mill. Now, depending on which side you use for your reference side of the part, you could have also put the angle of rotation up here and rotated from the other side. It would have worked as well. So now our angle of tilt, if I come back here and draw back in this side over here and draw this back into there, that is going to hit that at a right angle. So that's hitting this surface here at a right angle. This, of course, is a right angle because that's a vertical and a horizontal. The hypotenuse of that triangle cuts across here. So what that means is I need to find, back over on this drawing, this top view drawing, I need to find this length across here that comes and hits that edge at a right angle. There's my right angle. I know that R is 28.40 degrees, and I know that this side down here is 30.78. Now again, remember that 30.78, that came from us just picking 10 millimeters to be the depth. So that 30.78 is not a real dimension, but the ratio of dimensions are true. The angle, the 28.40, is the true angle. Even though our dimensions are hypothetical, that angle is true because the angles, similar triangles, similar figures have the same angle, even though the sides are just proportional. I need to find over here this side, which I'm going to label D. That is the opposite side from our angle. The 30.78 is the hypotenuse. So we're dealing with a sine here. Sine of 28.40 degrees equals that opposite side of D over our hypotenuse of 30.78. So again, we'll put that over 1, and we will cross multiply and divide. So sine of 28.40 times 30.78 divided by 1 is 14.64. That's 14.64. So back to our original drawing, that's saying this here is 14.64. And this here is what we chose down here to be 10 millimeters. So it gives us this right triangle in here. Draw down below. This is that 14.64 that we just calculated. And this, again, is our depth of 10 millimeters that we chose to start this calculation. What we need is right here. That is our angle of tilt. And what we have is our opposite side of 10, our adjacent side of 14.64. So we are going to use a tangent again. Since we're looking for the angle, it's going to be an inverse tangent of our opposite side of 10 over our adjacent side of 14.64. Second tangent, 10 divided by 14.64. We get 34.34. So our rotation here we're going to rotate that part 28.40 degrees. And then we're going to tilt the table or use a tilt vise, a tilt jig of some sort, to 34.34 degrees. Now, there are formulas in those packets that I have posted or that I've given you that allow you, just like with the drilling when we gave you the angles, that allow you to just take the angles and crank these out. I am really not a huge fan of those formulas. And we saw with the drilling that they did come from what we did here. If you want to use those formulas, feel free. I'm not going to run through them right now. But if you try to use them and you have questions, let me know and I will go through an example of them tomorrow. So now we want to switch to a different form of a compound angle. And we want to talk about what's called the intersection of angular surfaces. So what this is, if I can draw this, halfway is decent. So we're going to start out with our standard block here. And what we're going to do is we're going to cut an angle across here and here, and we're going to mill that surface off. So what we have done here is we have created one angular surface. Next, we're going to mill the other direction here. We're going to mill from here to here. We're going to cut that surface off. Obviously, this will come this way. But what you'll notice is since we're coming the same depth here, this will come like this and then angle down, gives the intersection of those surfaces. So what we want to be able to do here is describe the orientation of this line here where those two surfaces intersect. So again, what we're looking at is a box that contains that angled intersection there. It's really just a line of intersection from top back corner to bottom front corner. So this is basically an angular drilling issue. So if I know this distance here and this distance here and then the depth, I have everything I need to know to do this. So from the top view, this is going to look like this. And let's say that this is 2.10 inches here and 1.700 inches here. And I give you this here is 1.00 inches. And over here, let's call this 0.900 inches. What we're really concerned with, what we really want to know is this difference here and this difference here. So this difference here is 1.1. Just the difference between the 2.1 and the 1.0. This difference over here is 0.8 inches. Difference between the 1.7 and the 0.9. So that's telling us is if we draw our box here, This dimension here is the 1.1 inch dimension. This dimension here is the 0.8 inch dimension. Our front view of this is going to look something like that. And our side view or end view is going to look like that. A little bit better. And so let's say that I tell you that this overall height is 1.200 inches, and that this here is 0.500 inches. The dimension, again, that we really want off of this is this one here, which is the 1.2 minus the 0.5, giving us 0.700 inches. So this here is 0.700 inches. So I've completed my little box, and my surface I'm worried about goes from this corner to that corner. And so this would be if I'm just going to take that surface and line it up so I can run a grinder across it to just take off the burrs of that surface or to relieve the edge of that surface or whatever. I need to get that surface lined up so that I'm ready to hit it with whatever we're going at, even if it's just an automatic buffer that we're running over the thing. So we have that angled surface. Our rotation is still going to be at the bottom of this box. Right there's my angle of rotation. So I'm looking at this triangle. Here's R. This is the 0.8 inches, and this is the 1.1 inch down here. So R obviously is going to be using tangent. Looking for the angle, it's an inverse tangent of the opposite side of 0.8 over the adjacent side of 1.1. Giving us 36.03 degrees. My rotation. Now, rather than a tilt angle on these, typically what they find is they find this angle here, which we had defined before. I remember back last week, we defined that as angle A. That's looking on this triangle here. Angle A is from the bottom. We know that this is our depth of 0.70 inches. Right now, that's all we know about that. When we did the drilling, we had the length of this surface here. Remember, that was the length of our bore. Let's go ahead and find that length. Remember, to find that length, we use that three-dimensional Pythagorean theorem. Square root of 1.1 squared plus 0.8 squared plus 0.7 squared. Which gives us 1.529, 1.530. Inches is the length of that surface. That's actually the length of this surface right here that we have highlighted in purple. So now we can find A, because we have the opposite side and the hypotenuse. That's a sine. So A is an inverse sine of the opposite side of 0.7 over the hypotenuse of 1.530. Gives 27.23 degrees for that angle there. So that's describing that surface. So remember, A would not necessarily be the angle of tilt here. It would be the angle that describes the orientation of the surface. And actually, in this case, it would be the angle of tilt if we're trying to bring that surface into a position to be either ground, a relief grind, or a buffing to smooth it off. Well, in this case, I gave you the dimensions for these. How does this change if I give you different information? And instead of giving you just the dimensions, from the front and side views, if I give you this angle, let's say I tell you that this angle here is 36 degrees and this one here is 41 degrees. Well, once again, just like any other of the problems where we were only given angles, we can make up one of our dimensions. We can guess one of the dimensions and use that to find everything else. So once again, I'm going to guess a depth, and I'll put that in as 10 millimeters. Now, I've been asked before, how do you know that that's measured in metric and not standard? Again, the answer is it doesn't matter. I could have said 1 inch or 10 inches or whatever. It doesn't matter what the units are. Remember, it's that ratio of lengths is all that matters in these situations. So I can find this dimension here, which I'll call dimension A, and this dimension here, which I'm going to call dimension B. So the triangle I'm actually working with looks like this, and this is the 36 degrees. There's my right angle. I have the opposite side and the adjacent side, so I'm dealing with a tangent. The tangent of 36 degrees equals the opposite side of 10 over the adjacent side of A. So I'll put this over 1, and I will cross multiply and divide. So 1 times 10 is 10, divided by the tangent of 36 degrees. Gives us 13.76 for that dimension A. Dimension B. Well, here's our triangle right here. There's my right angle. This is 41 degrees up here. Again, I have opposite and adjacent, so it's still a tangent. So I'm going to do a tangent of 41 degrees. Equals my opposite side of 10 millimeters over my adjacent side of B. And once again, I put that over 1 and I cross multiply and divide. So 1 times 10 is 10, divided by the tangent of 41 degrees. Gives us 11.50 millimeters is our dimension B. What this means is looking at a box here. Go away. This dimension here is 13.76 millimeters. This dimension here is 11.50 millimeters. This dimension here is 10 millimeters. And our angular surface here, our intersection, goes from here to there. Our angle of rotation is right here on the bottom edge. So this is R, 11.50 and 13.76 on that triangle. What we have here, according to angle R, is the opposite side and the adjacent side, so we're dealing with a tangent. We're looking for the angle, so it is an inverse tangent. The opposite side is the 11.50. Really? Exactly 11.50 it is. Over the adjacent side of 13.76. Second tangent, 11.5 divided by 13.76. Gives us 39.887, 39.89 degrees. Is our angle of rotation. That came off of this triangle down here. Our angle of tilt will come off of this triangle up here. And it's really not an angle of tilt. We're calling it angle A for right now. We know this dimension over here is the 10 millimeters that we chose, but we don't know any of the other dimensions. But we can find this hypotenuse here using our three-dimension Pythagorean theorem. That's the square root of 13.76 squared plus 11.50 squared plus 10 squared. Giving us 20.53, 20.533 we'll call it. I'll just go 5.3 millimeters. And now from angle A, we have the opposite side and the hypotenuse. So it's going to be sine. We're looking for the angle. So A is going to be the inverse sine of our opposite side of 10 millimeters divided by our hypotenuse of 20.53 millimeters. The second sine 10 divided by 20.53. We get 29.15 degrees. There's my angle of rotation in angle A. My rotation, 39.89 degrees. My angle A, 29.15. So very similar to what we've worked on in the past. So I want you to keep working on that stuff from yesterday. I'm anticipating we didn't have time to finish those up. We're going to throw on top of that now in that packet, page 416 through 418, 1 through 14. 1 through 13, the odds, we'll say. So tomorrow, we'll go over another example or two of this, and then we will review all of our types of angular drilling. Thursday is unit test. So it'll be our test on the angular drilling. It's already out on Blackboard. If you would like to download it and get started on it, please feel free. So Thursday, I will be in class again as normal, but we won't be presenting any new material. So if you guys log in, I'll be here to answer questions, on the test, but there won't be any new lecture or homework Thursday again. Then next week, as I said, we're going to look at solution mixing, like for coolant solutions, and maybe do a little bit of basic statistics of what you would need for your basic statistical process control calculation. So with that, I'll let you guys have the rest of the day here to get started on your homework. So we'll shut off the recording and let you guys get to work.